you already know the title, so I'll just continue from here. The main hypothesis, in fact, I've misspelled this, that I'm going to offer you and offer tests, and you may decide whether you accept, is that removal of cold, dense mantle lithosphere beneath Tibet, beneath the Tibetan Plateau, 15 to 10 million years ago, raised the surface of the plateau 1,000 meters approximately, and created high surrounding topography. That's the hypothesis. And we know a lot about the evolution of this area, so let's start with some background. On the left, you see the Tibetan Plateau and reconstructed positions of India, where the northern edge of India just follows the foot of the Himalaya. This isn't the real northern edge, but we don't know where that lay. And this shows positions going back in time, 10, 20, 34, 40 million years, back to 69 million years ago. This is where India lay. Plotted as a function of the distance on this axis and the age on this axis for the northwest corner, that corner, and the northeast corner, this one, what you see is India moved northward rapidly at more than 100 millimeters a year until sometime near 50 million years ago. I don't want to dwell on this much, but the rate slowed down. Presumably, India collided either with Asia or with an island arc near it, continued to move north, and still continues to move north, but at a slowing rate. I think we know this. Nobody's going to doubt this, to my knowledge. I hope not. Now I'm going to show this only once because many of you have seen it. This is an animation made by Tanya Atwater, a cross section through the earth. This is India. This is oceanic region between India and Asia 60 million years ago. The southern edge of Asia, a line of volcanoes marking an Andean belt. The tan color, I've lost it. This is crust. The red underneath is mantle. Crust is thin under the oceanic regions. The mantle, the darkened area, is mantle lithosphere. And when I start this, India will move north, and two features to notice. The Himalaya is built of slices of India that are thrust back on top of India, and the Tibetan crust across this region, this whole region will become shorter in the north-south sense and thicker to become the Tibetan Plateau. Those are the two main features. So there goes India. We're now at 50 million years ago. India collides. A new thrust fault will break through here, and another one will break later. Meanwhile, the crust under Tibet thickens, and Tibet becomes a narrower zone. Tarim Basin has not thickened, a bit of thickening in the Tian Shan. Now, the most speculative aspect of this are these drips of mantle lithosphere that have come off. Tanya made this for me because this is what I think. This is the hypothesis we're testing. This could be false. I don't contend that it's necessarily right. So I'm just not going to show it again, or I'm going to try not to show it again. I guess there we go. So let's start back in the early Cenozoic. I'm going to show you a few places, just a couple of places, where there's no question the crust was being shortened and thickening. This first area in the north, in the Hushul Basin, northern Tibet. This is a study by Steisch, Nimi, Clark, and Hung. And what they showed, they dated some of the thrust faults in here. They were able to date when slip occurred, and there was thrust faulting in this region between 43 and 47 million years ago, or since that time. It seemed to stop around 34 million years ago, and there's no evidence that it continued past 27 million years ago. So crustal shortening in here, thrusting both southward over thrusting and northward over thrusting. I'm going to move down a little bit farther south in this area. This is a study now by Kapp, DeSalle, Garrels, Heisler, and Dinglin in China. From this area, and I'm just showing you a cross-section through the Nyima Basin in this area, south on the left, north on the right. The yellow colors, these are tertiary sedimentary rock. The other thing, Jurassic and Cretaceous, and you see a number of thrust faults in here. This is a particularly large thrust fault in this area. Other thrust faults, a lot of crustal shortening. Much of this occurred in Cretaceous. The minimum total shortening post mid-Cretaceous, 58 kilometers, is 47%. That's a large fraction. The tertiary part is smaller, the part that can be defined for sure to be tertiary, 25, but still almost 30% shortening. And if we take a step back here, this is now from the same paper by Kapp and his colleagues, looking from the south, the Himalaya down in here, the Tethyan Himalayan belt, up in the north, not all the way, Fenghuoshan is in the Hushil region. And if we're back at 50 to 30 million years ago, much crustal shortening in the Jiangtong up in this area, 25% shortening. That's what I showed you. The Nyima Basin is actually a very narrow area, and they argue that all of this shortening stopped by 25 million years ago. So crustal thickening within Tibet until roughly 25 million years ago in this area. Now, this is a study that I don't think has been appreciated enough. Wu Junhan and his colleagues. And what they mapped were lake sediments, and they argue these are interconnected early Miocene lakes. So all of these green areas, they're the same age lakes spread across northern Tibet. This is the Hushil Basin. Just to locate you, the Kunlun is up here, further north is Golmud, Lhasa is down here, and this road is the main road that connects the two of them. On the south of the side of the Tongha, again, lake deposits in the Lumpala Basin and further west in the Nyima Basin and others. And their point is that there were widespread lakes and essentially no deformation of these. There are very little deformation since early Miocene, not a precise date, but since early Miocene. And now a summary going back to Steisch, Nimi, Clark, and Hung, a map of Tibet, a cross section starting at 27 south, someplace down here, going all the way to 40 north. 40 north would be way up here in the top of this picture. And these are ages on this axis, 100 billion years, 80, 60, 40, 20. And when there was action, when there was activity, or more precisely, when there was thrust faulting. Thrust faulting continues in the Himalaya. Thrust faulting continues in the Chilianshan to the north, but most of this thrust faulting is ended in the central part, maybe as early as 45 million years ago, a little younger on the two flanks in this area. But thrust faulting across Tibet and ending at different times in different places. Okay, the big point of this, one of the big points of this talk is that this development changed 15 to 10 million years ago. The Tibetan crust stopped thickening by this time, and the plateau began to grow wider apart, grow outward, spread apart, become a wider plateau. The crust thinned. This is an important part of this story. And because of isostasy, its mean elevation began to decrease. The best evidence for this happening is present-day earthquakes. Most of you are geologists, you'll understand these plots. The blue show normal faulting. Normal faulting when you extend the crust and one block drops down. The red show thrust faulting. Thrust faulting when one block is pushed over the top of another. And the black ones are strike-slip faulting. Let me just say this, if you don't understand this, just trust me. Both the normal faults, the blue ones, and the strike-slip faults show east-west extension, approximately east-west extension. And the normal faults require crustal thinning by this process. The strike-slip faults don't. So there's east-west extension and there's crustal thinning. The normal faults are all at high elevation. This is a plot of elevation, 5,000 meters. One exception, this one out in here, let's not worry about it. The thrust faults are at lower elevations. Well, the important point is normal faulting cannot build a high plateau. So this normal faulting that's happening now after a long period of thrust faulting means some change must have occurred. There must have been a change. You haven't had normal faulting throughout the development of the plateau. And this change is the main focus of my talk. When did that happen? So now this is what's the onset of east-west extension of the plateau and crustal thinning. And these are places where groups of people, groups of geologists have come in and dated this. In this area, 13.5 million years ago, the normal faulting began. In this area, 13 million years, 15. Then you work your way around, and these numbers are all in the range of roughly 15 to 10 million years ago. Normal faults all through this area. These are north-south grabens with east-west extension in all cases. Grabens, they require crustal thinning. Today, if one looks at the GPS field, Go Wei Peng's work, this is plotted relative to India, So these arrows are pointing towards India. The difference between the white and the red is just a scale change. The white ones are so fast that if they were all plotted with the purple arrows, they'd obliterate one another. But the key fact is that if you look in the west out here, there's a westward component. These are moving westward. If you look in the east, there's an eastward component. There must be extension in this region, an inescapable conclusion. In fact, if you extrapolate the present day strain rates that you deduce from the GPS back to 10 to 15 million years ago, this is a big assumption, assuming a constant rate over that period of time, but not unreasonable. And you assume area isostasy, again, a completely reasonable assumption. This means you have a drop of 1,000 meters in the mean elevation of Tibet. Said in other words, Tibet now, roughly 5,000 meters, most of the area would have been 6,000 meters high, would have been 1,000 meters high. It would have been a bigger, higher plateau, or not bigger, but higher plateau than we have today. And that's just a logical conclusion that follows from simple assumptions. So a major change occurred. Between 10 and 15 million years ago, the crust stopped thickening, began to spread apart, the crust thinned, the plateau grew outward, becoming a wider plateau. I hope you get all this exaggeration. And the mean elevation began to decrease. So why did this happen? So the hypothesis that I'm offering, and that some of my colleagues also like, but not everyone, the hypothesis is you start with crust, which is buoyant, above mantle lithosphere, which is negatively buoyant, above asthenosphere. The mantle lithosphere is slightly more dense than the asthenosphere, at least at the same pressure. Crust is, of course, much less dense. You thicken this horizontally. You build a high plateau with a root, crustal root, because of area isostasy, but you also thicken the mantle lithosphere. And this is higher density, more dense than the surrounding material. So this is unstable. This is an unstable region, and gravity wants to pull this down. Gravity will pull this down, and if it can, it will remove that. So let's let it remove it. This region is removed. The light blue is showing you heavy material that's been removed. You remove dense blobs of mantle lithosphere, call it deblobbing. That reduces the load on the base of the lithosphere, and the surface rises. So you take this off, and the surface goes up. The green is showing you the increase in elevation. This is a small fraction of the total elevation of Tibet. Small, 1,000 meters, maybe 2,000 meters, but 1 or 2 out of 5,000 meters. By no means the whole plateau. Moreover, what this does is it gives the region potential energy, puts potential energy into the lithosphere, and that can do work. And I'm using the term that Lorentz, the atmospheric scientist, used. And so what happens? The surface will subside because the crust will extend, and the potential energy that's given will power this extension, but the flanks, you'll still have thrust faulting. So the surface will go down, but the flanks will expand and grow outward. This is the logical conclusion that comes from removing this material and then letting evolve afterwards. So removal of mantle lithosphere beneath mountain belts and plateaus, what does it predict? Well, it predicts lateral variations in density and seismic wave speeds because you've removed this cold material and taken it away. Enhanced volcanism, you've removed this, you've brought hot material to shallow depths in here where it can melt. You've thinned the crust, we talked about that. Outward growth of the range will grow outward where thrust faults occur today. There'll be an increase in the surface elevation because of the removal of this cold, dense material. And then, because of the extension and the crustal thinning, this will be followed by subsidence. So I'm now going to go through a fraction of the data that bear on this to give you arguments that show that what we know, all of what we know passes these tests. Just because it passes a test doesn't make it right, but it passes the tests. So this is a map of PN speeds across Tibet and its surroundings. PN is the P wave that travels at the base of the crust in the uppermost mantle. And a simple rule of thumb, if the speed is greater than 8.1 kilometers per second, you have cold, dense upper mantle. And if it's slower than 8.1 kilometers per second, you have warm, low density upper mantle. Northern Tibet, So here, this is the Himalaya down in here. You'll recognize the boundaries of Nepal, the Tarim Basin in here, the Tian Shan. Northern Tibet has low speeds, southern Tibet has high speeds. So you have lateral variations in P wave speeds, lateral variations in the upper mantle. I'm going to dwell a little bit on this because I consider this to be a particularly good study. This is a study by Tsung Chen and Noack across southern and western Tibet in this area. These are the locations of their stations. And what they used is S waves. This path, if you have a station and a distant earthquake, the S wave would come up, come to the moho, the base of the crust, and come to that site. But in addition, an S wave can come up, pass through the crust, bounce off the surface as a P wave. This happens, of course, all the time. But in the right distance range, that wave is totally reflected. It doesn't go back into the mantle. It reflects off the backup station. This is an S, P, M from moho, P phase again. And obviously the difference in time between the direct S wave and the SSPMP phase depends on the thickness of the crust. A thick crust, a long duration between them. A thin crust, a short time between those two. So here we have seismograms. Plotted here is time. They're all lined up on the arrival time of the S wave here. Time increases downwards. This is the array going across from south on this side to north on this side. So these stations going up in this region, up in this direction. As I said, they're lined up on the S wave. And here the red triangles show the arrival time of this SSPMP phase. And you can see it's earlier in the south than is in the north. And the difference is substantial. It's a couple of seconds difference in here and easily seen. You can see these are very different. If you convert that into crustal thickness, you have this plot, which I'll show in the next slide because it's easier to see. Crustal thickness, here's a scale going down 50, 60, 70, 80 kilometers. In southern Tibet, the crust is 75 kilometers thick. In central and northern Tibet, it's only about 65 kilometers thick, 15 kilometers. That's a huge difference, especially given the plateau is quite flat. The surface is the same height everywhere across here. So the only way this is possible to have this and have isostatic balance is that the thinner crust in the north, but similar elevations, means you have to have a hotter upper mantle in the north than the south. This is an inescapable conclusion. So in the context of tests, lateral variations in density and seismic wave speeds, I haven't shown you all the data by any means, but data support that. What about enhanced volcanism? Well, first a map. It's going back to Dinglin, back many years ago now. A map showing all of these greens, reds, and yellows are sites of volcanism, but let's concentrate in the north. The numbers are ages. So 3, 1 to 10 million years, maybe 1 million, 16, that's the oldest, 14 to 9, 13 to 7. This is all in that range of 15 to 10 million years in age. Lots of volcanism in here. And if you go into this part of the world, especially if you're stuck in the snow and you have to spend some time, you see capping the hills just about everywhere. They're not everywhere, but in many places, there are basalts capping the ridges in northern Tibet. This is a common sight. Again, this is quite a long distance of nothing, just flat dirt. But again, black rock basalt capping the ridges. And one more in this area. This lake hasn't quite yet frozen. Basalt capping the ridges. Basalt is widespread in northern Tibet. So enhanced volcanism. What about crustal thinning beneath the plateau? I somehow have smeared my slide. Oh, there it goes. We've been through this, the normal faulting. This is showing you, this of course is part of why we hypothesized what we've hypothesized, but there's no questioning that crustal thinning beneath the plateau occurs now. Outward growth of the range. I'll show you a few examples of this from different areas. Let's start with the Tian Shan up in here. The next slide is just going to blow up the topography of the Tian Shan. So it'll blow up. Here's a scale, 300 kilometers. Geologists, mostly Soviet geologists on the former Soviet Union side up in here, have measured at least 50 kilometers of shortening, but there's much that they can't see. If you add up the amount of crust in this region and assume it's all due to thickening of crust, then you get to maybe 200 kilometers of crustal thickening. This is work of Jean-Philippe Avoic, Paul Taponnier, and others. So about 100 kilometers, 200 kilometers maximum crustal shortening. Well, GPS shows it's very rapid shortening across the Tian Shan, 20 millimeters a year. Here's the scale, 10 millimeters a year down here. And you can see this Tarim Basin is moving north at 20 millimeters a year relative to the Kazakh platform in here. This rate is the same rate as what we have within the Himalaya today. The rate of underthrusting beneath the Himalaya is also about 20 millimeters a year. This is fast. If you take that 200 kilometer estimate of the amount of shortening across this region and divide it by 20 millimeters a year, which is the same as dividing by 20 kilometers per million years, it means you're less than 10 million years to make the belt. The belt is younger than that 10 to 15 million year range. Indeed, there certainly was topography before this time, but the point is most of this area is young. And the logic here is you've thrust up the Himalaya, with thrust faulting, you've built the Himalaya, you make a high Tibetan Plateau where the pressure is high. Well, if you can get that pressure up, you drop the pressure, cause the shortening further north. I should say when we drew this, Paul Taponnier drew this picture, we had a different interpretation with this, but we won't worry about that now. Let's look on the northern edge of the Tian Shan back 9 million years. Again, Zheng Dewan and colleagues. And looking now from the southwest on this side, sorry, I didn't mean to do that. On the southwest side, northeast side, you have Paleo-Proterozoic granite thrust on top of sedimentary rock, Paleogene, early Neogene sedimentary rock reaching up into Neogene Quaternary. This thrust fault is active. What they did was to take samples of this granite at different elevations and date when that rock cooled below a temperature of 60 or 70 degrees using uranium, thorium, helium dating. And what you see is at the top, when you're at high elevation, as you come down, the ages become much, much younger until you get to 9 million years, and then all of a sudden, bang, everything cools rapidly. This rapid cooling near 9 million years is consistent with thrust faulting beginning at that time and erosion then accelerating. It's the erosion, of course, that led to the cooling, but this rock didn't cool until it became high enough and accessible to rivers that would erode it, and that's 9 million years ago. Let's go south of India. Here's India, Sri Lanka. We're looking at the 90 East Ridge along in here, and you can see hints of east-west belts this is actually superimposed on the gravity field. So the gravity is showing you something about the topography. And I'm going to show you a cross-section across this region, cross-section through a part of this. The bottom is the topography. You see sediment where it's flat, you see sediment in here. Basement rock poked through, this is a multiple reflection, don't worry about that. Basement poked through over here, basement just barely poked through in here. But in fact, even basement rising up in this area underneath thick sediment. And the gravity shows you the same thing. Where you have dense rock against water, you have a positive gravity anomaly. Where you have dense rock surrounded by sediment, you have a smaller positive anomaly. And again, and note the scale, 200 kilometers. So this is widespread, very minor folding within the Indian lithosphere. The amount of shortening across this is small. But again, when did it start? Well, the deep sea drilling project went out here and found folds in the sediment. In fact, one emerging above the surface, bounded by almost surely by thrust faults dipping underneath. The scale doesn't allow you to see the vertical exaggerated scale doesn't allow you to see the thrust faults. And if you take the horizon, they say it's horizon A, that comes in that marks the end of sediment being buried at a constant rate with the onlap of sediment filling in this basin, they date that at 7.6 million years ago. So 7.6 million years ago, this folding and this deformation began. Again, after this 10 to 15 million year age that we've given to Tibet. And one last one, Marin Clark and her colleagues working around over in here, the Dadu River, the Yangtze is down in this area. And again, this is thermochronology. They've looked into deeply incised canyons in here. And what you see again, when you're near the surface, and here they're projecting depth below the flat surface, which they treat as a plateau in here, perhaps wrongly, but let's not worry about that now. Going down 4,000 meters. So the elevation of the surface here is at least 4,000 meters because the bottom of the valley is above sea level. Ages increase rather gently, or I should say the ages increase rapidly with depth because this is slow cooling. These ages are dating up when the rock was approximately 2,000 to 3,000 meters below the surface. So you can look at these ages as saying the surface lay 2,000 to 3,000 meters above, and gradually that surface moved down. And then all of a sudden at this time, around 10 million years ago, suddenly you incise the canyons. And their interpretation is that this region rose at that time. So you can't digest all of this. This is a collection from the Tian Shan, their evidence doing for ages of, in this case, sedimentation, in this case, rapid erosion, starting at times between 15 and 10. Even the opening of Lake Baikal seems to be in that period of time, going all the way around the Shillong Plateau. This plateau in here would be sometime between 14 and 8 million years ago when it started to emerge, the Indian Ocean floor down in this region. So you can't digest this, but these numbers are all in the same range. And so I would argue the outward growth of the range accelerating around 10 to 15 million years ago passes plenty of tests. What about the surface elevation? This is where my own opinions have changed quite a bit in the last few years because of some beautiful work done by others. But first, I want to dispel some old views, some of which are right, but some of which I think are wrong. And that's paleoaltimetry constrained by delta 18O, oxygen 18. This is a profile, topographic profile across Tibet. Down here would be the plains of India, peaks of the Himalaya coming across. And this is delta O18 measured against mean ocean water as the reference. And on a profile going from 1 degree south, this is degrees north of the Himalayan crest, so 1 degree south, the crest would be here at 0, and 10 degrees away. So this is well into northern Tibet. This is modern data, rainfall. The oxygen 18 values plummet, go from -8, -6, down to -20 when you climb up over the Himalaya, but then they return in some way. This is important. What do you do if you have a sample up in here if you measure oxygen 18? Well, you don't say that this site is at the same elevation as this site because you're completely wrong. What's gone wrong with this? This is work, this slide is taken from a recent paper by Bob Spicer and some of his Chinese colleagues, but I got this also from a paper by Deng and Jia. It's a couple of years older. I feel very stupid that I had to be educated as late as 2018 on this, but I'm going to give you a story that all of these agree on. And the interpretation of oxygen 18 always rests on the assumption of Rayleigh distillation. And here, the logic is as air cools, the moisture condenses, and the heavy isotopes rain out first. They go into the condensate, and then they go into the rain, and they rain out. The other part of Rayleigh distillation is rain out occurs only once. So once you've lost that oxygen 18, it's gone. You can't do anything. And this means as paleoaltimeters, delta O18 records the highest elevation along the path. And so if you have a site in here, let's just look at this. I'll blow this up in the next slide. In fact, if you have a slide in here, a site here, first, if we look back here at the Trans-Himalaya or the Himalaya, the moisture's coming up, the air is cooling, you're raining out, you're depleting oxygen 18. So large negative values of delta O18 in this area make sense. Over here, I would argue now that I'm smarter than I was, large negative values also make sense. They make sense because the rainfall that falls here became depleted in oxygen 18 when that moisture crossed the Trans-Himalaya back here. So in this area, delta O18 tells you nothing about paleoaltimetry. That's the argument I want to make, and I'm sure I've now angered a bunch of people Most of them maybe not in China, but anyway, I probably have. Okay, I want to turn to three basins, the Lumpala, the Nyima, and the Gyertse basins, which are in the southern part of Tibet. This is the Indus-Tsangpo Suture coming across here. This is the boundary between Indian rock and Asian rock, Tibetan rock, but Southern Asia before the collision. And unfortunately, this first one I want to look at, I can't show you what I'd like to show you because I don't know how to do it. But this is from a paper, and I'm showing this in part because when this paper was published, I didn't believe it at all. We're back in 2016. I didn't believe it. Low paleo elevation of the northern Lhasa terrain during the late Eocene. Fossil foraminifera. They're arguing these are marine fossil, marine foraminifera found in the Gyertse basin, and stable isotope evidence. The stable isotopes are not highly depleted in oxygen 18 at all. They look like plains of India type examples. So this is the Gyertse basin. The Trans-Himalaya, the Lhasa terrain coming across here. The Himalaya itself lies down in here. And they're arguing that back in Eocene time, this area was at sea level. This was not received well. And as I said, I didn't believe it, though not for good reason. It just didn't fit my worldview. I now think they made a good point. I've changed my mind. If we go over to the Lumpala basin, this basin in here, this is just published just within late December, in fact, of 2020. They found these magnificent fossil leaves, big, nice leaves with smooth margins around the edge. Smooth margins around the edge are common in low latitude, warm environments. Margins with teeth are common in higher latitude, temperate environments. But most of these have smooth margins. Here's another one with a smooth margin. These are flaws in the fossil, but you can see a smooth margin, a fairly smooth margin in these. And these can be analyzed. There's wonderful work that's been done over the years in using these to get at paleoclimate. So taking this work, what's plotted here is mean annual temperature versus what's called vector score. Each of these dots is from a modern forest somewhere in the world. And a lot of analysis has gone into this where they've looked at leaf shapes, leaf sizes, many characteristics, come up with a statistical description that plots, that varies, the vector score varies with mean annual temperature. And this dot with an error bar shows the fossil data from the Lumpala basin, which gives it a 19°C temperature, which would put it around 1,500 meters. They can do better, though. One of the problems with this method is temperature is a risky quantity to measure. So leaf physiognomy, this is the shapes and sizes of leaves, and altitude. What do we? You can leave the margin. You can use the leaf margins and sizes, but you have to measure something that depends on elevation and temperature. Temperature depends on height in the atmosphere, but it's not a good measure of temperature at the surface as you wander around the surface of the Earth. So this is not, temperature is not really what you want. It's not bad, but that's not so good. Pressure would be better, but leaves don't care about it. And so what's used is moist enthalpy. So what's moist enthalpy? First, there is a quantity, moist static energy, it's per unit mass. This is conserved in the atmosphere as parcels of air move around in the atmosphere. Of course, radiation will change this, but that's a slow process with a time constant of weeks. Moist static energy is the internal energy, the heat capacity at constant pressure times the temperature, plus the latent heat of vaporization times the amount of water vapor in the atmosphere, plus the potential energy, G times the height. Remember, this is per unit mass. That's why there's no mass in this. And this quantity is conserved as air parcels move. Now, there's another way of writing this. Moist energy can be written as this of moist enthalpy plus potential energy, where the moist enthalpy is the sum of these first two terms, the internal energy and the latent heat. And this is why this becomes useful. To look at this, if moist static energy is conserved, the moist static energy here and the moist static energy here will be the same. But down here at sea level, the Z is 0, And so the moist static energy is simply equal to the moist enthalpy at this elevation. Whereas in the high region, the moist enthalpy will be different because the moist static energy should be the same as over here, but you have this height. So you can convert this. This is just algebra, right? The height is the difference in moist enthalpy, which we infer from the plants, and which I say we, but Tu Sao and his Su Tao and his colleagues have done. And then you take that difference and divide by gravity, and you get an elevation. So again, similarly, all these dots are modern forest data that have been converted into some vector score that is perpendicular, oriented in this multidimensional space to moist enthalpy, where these are increasing 300 in kilojoules per kilogram. The moist enthalpy for Lumpala is 326, for sea level 341. Gravity, 9.8 meters per second. In this business, that's 10. And I changed the units on you. You'll never have seen gravity expressed in those units. But if you do, then you simply take the difference in moist enthalpy, divide by that number, and you get a height, 1,500 meters. Same height that I gave you before for the temperature. So what this says is, from these leaves in the Lumpala Basin at 47 million years ago, the height was 1,500 plus or minus 900 meters, much lower than the present day 4,500 meters. Okay, a little bit more recently, at 25 million years ago, again, the same Su Tao and many colleagues found fossils of palm fronds. Note the scale, 10 centimeters. This is a 50 centimeter long palm frond, a fossil of a palm leaf. Palms cannot survive temperatures below 5 degrees C, or approximately 5 degrees C. So that's saying the Lumpala Basin was below 2,000 meters or so, a little higher than 40-some million years ago. But at 25 million years ago, it's still half its present day elevation. It has to have come up since that time. And when they take this and they put this in their interpretation back Paleocene, Eocene time, the Lumpala Basin would have been quite low, around 2 kilometers. Oligocene still around 2 kilometers, but then it's come up since that time, and then you're up to this modern elevation up in here. I accept this. I find this work very good. So here's a couple of cartoons from the paper by a recent paper by Spicer. For Cretaceous time, you have an ocean south of the Trans-Himalaya. Down here, this was clearly above water. But again, probably a shallow sea south of the Zhangtang in the central part of Tibet today. By Paleogene, the ocean was gone, except maybe it wasn't gone in the Gertsa Basin, but you had a low area between these high ranges. And then when you finally get to Neogene time, the whole region has become high. They're calling this the Himalaya, but I would rather call it the Trans-Himalaya. My own view of this, which is based on their work, and also a nice summary from Deng Tao and Ding Lin from back 6 years ago. My own view is that if you look 40 million years ago, you had a basin in here. I don't know how wide it was, the Lumpala, also the Nyima, the Gertsa Basin. When you get to 25, it's still quite low, separating these areas, and then the whole region has come up since that time. This is different from what I used to think, though I'm not sure I know or even remember what I used to think. Whatever it was wrong. Okay, so we've argued that there's been an increase in surface elevation since 15 to 10 million years ago. What about followed by subsidence? Well, one last one. These are a whole collection from Ding Lin's work a few years ago. The blue is showing you sites in Tibet. These are sites like Nyima, Lumpala, I can't remember the name of it, Namling in here, and then some sites from the Himalaya itself. I don't want to focus on anything more in this but one site, Namling. Namling is this site N, where years ago paleobotany showed an elevation similar to what's shown here and stable isotopes. This was an area where you're close enough that stable isotopes, I think, give you a reliable elevation. And they gave an elevation of 5.5 kilometers. And what's important to me here is the present day elevation is down here. So you've had a 1,000-meter drop since 10 to 15 million years. One site doesn't prove the whole plateau did this, of course. So increase in surface elevation, then followed by subsidence. So what's going on? Well, I'm showing you here two cartoons, two among many possibilities. You'll see they have one thing in common, that's my name. I don't know what's going on for sure. This was drawn with the idea that you subduct India under southern Tibet, Tibetan Plateau across here. You draw cold material, it sinks. You have hot material in the north. Indeed, you have low P wave speeds, low S wave speeds in here, higher speeds in here. You have thinner crust in the north. That fits. But an alternative is you have drips, just drips coming off and they're ponding at some depth in here. Can we study this? Can we address this? And the answer is we can. Can we answer this question? I hope so someday, but what I'm going to show you is not going to give you an answer. So plotted here, the top are P wave speeds, 100 kilometers for this one, 200 kilometers for this one. And what this is really showing is that it's high speeds around the southern edge, but lower speeds within the plateau. These aren't really very reliably determined, and I don't want to focus on this. I'm much more, I want to focus more on the S waves. So this is S waves determined from surface waves at 100 kilometers and 200 kilometers. And what you see is high speeds, presumably cold material under the Himalaya and southern Tibet, and low speeds in the north. And as you go deeper, this high speed region encroaches in, but you still have that low speed region in the north. So what do we get from tomography? I'm going to show you, I think it's 4 different studies, and you can choose what you like if you want. This was one of the early ones. This is a network of stations going across the middle of Tibet, so you'll recognize there's the boundary of Nepal and the Himalaya are down here. And they came up with this image of high speeds, blue giving high speeds, red giving low speeds, ranging from about 1.5% high speed. This is plotted not as speed, but as slowness, the inverse of speed. So blue is high speed, even though it looks negative here. And the red is low speed. And so a difference of 3% across the whole region. Not huge, but not negligible by any means. They have this picture and they drew this cartoon image with India lithosphere thrusting down and then somehow sinking down in this region. Well, a few years later, oh, sorry, this is then their cartoon image of this, the cartoon image that it was poorly shown before, India under thrusting beneath here, and then the Indian lithosphere plunging underneath, and maybe this kind of circulation in the north. So this is the Bangong Nujang Suture. This is right through the middle of Tibet. This is Lhasa in the southern edge, and of course, then you're getting into Himalayan terrain over in here. So a couple of years later, a study, a bigger study, global study, Lee, Vanderhilst, Meltzer, and Engdahl, they came and they used all the data from this paper, plus lots of other data, because many other networks had put in, and they got an image shown here. And at first glance, you say, well, they look alike. You see this cold region dipping to the north, you see it again dipping to the north. But let's take a closer look at this. These folks, Lee et al., used the same data that these guys used, but more. But here, the high-speed zone goes from about 150 kilometers down to about 350 kilometers. Lee et al. Say, well, no, the high-speed zone starts at 300 kilometers and goes down to 500 kilometers. There's almost no overlap in these. If you look on a map, of course, this area is not underneath that. It's shifted off to the side because this is just along the line. But the point here is that, what do you believe? That's your problem, not mine. I know what I believe. Okay, so another one. Here's again Tibetan Plateau, and here are 4 maps. Again, notice the title of this paper, Lithospheric Foundering. So they're foundering, that means essentially blobs sinking, or a big blob sinking into the mantle, below the mantle lithosphere. You'd think I might like this. So 80 kilometers, again, the low speeds in northern Tibet, higher speeds in the south. If you go down to 175 kilometers, the low speed region shows up as lower speeds, though not terribly low. By the way, the red dots are younger volcanoes, volcanic rock, and the yellow dots are older volcanic rock. And again, a high speed zone in here with a hint of some kind of funny thing in here. 350 kilometers, you got a circular blob. It's not small. Notice that's more than 500 kilometers in radius. That's not just a little drip. And all the way down to 500 kilometers, you see this. The next slide is going to show a profile along this line across through this whole area. So if I show you that, this is a profile, again, as I said, across this area. You see this blue, this high-speed region plunging down, going all the way down to 600 kilometers or maybe more, rather circular in shape. Well, that's completely different. Well, is it completely? It's very different from what I just showed you. Maybe it's right. So let me show you another one. This is Renenshen. This is now a study in this, it's really this box over in here. I'm not sure why I drew that red box. I think I drew that for some other region, but their study is this yellow box in here. And this is P on the left, S on the right, going down. So P wave and S wave speeds going from -1.5 to +1.5 for P and -3 to +3% variations in speeds. And what you see are zones of low speed, the red, zones, the blue, zones of high speed, and they're pretty continuous with one another. These blobs look like those, and they kind of continue as you go down. Maybe they're going by this depth. Again, the S waves showing you something similar, the blue underlying the blue. And so I would ask, are these blue areas, do they show blobs of sinking material? That's the way I want to interpret this, but I don't know whether I should or not. And the P and the S, they kind of agree with one another. Why not? Tomography beneath flat Tibet. Most show low speeds in northern Tibet. Otherwise, they disagree with one another. So as we say, pay your money, take your pick. And if we go back to this, this is the image. These are the images I want to leave you with, that mantle lithosphere has been removed, maybe in one big downward sinking region in the south and thinning of mantle lithosphere in the north, maybe thinning across mantle lithosphere by blobs, but and maybe by some other process. I don't know what it is, but I think we don't know. So if I summarize what I've tried to tell you, there's been a change from crustal thickening to normal faulting at about 15 million years ago, and this is best explained by removal of mantle lithosphere. This is not a unique explanation, but it's the least implausible one as far as I can see. And I've given you many tests of this hypothesis, and they pass. Maybe there are tests where this fails, but I haven't seen them yet, and maybe I'm just stubborn. The surface uplift of the Lumpala, Nyima, and Gertsa basins, and maybe the Hushul basins since 25 million years ago, agrees with this idea. But it's not very strong agreement. 25 million years is vague. I would rather see this closer to 15 million years to make it agree with what I've argued here. And this is only part of Tibet, of course. So this is, in a sense, the hypothesis passes this test, but this is not a strong test. And then finally, seismic topography can be found to match any hypothesis. Whatever you want, I'm sure you'll find data that can fit. So that's the end. But rather than leave you with these words, I just leave you with this view looking across from Lugmustag. You're looking about 200 kilometers away up here at the mountains up in here. And I am finished with what I had to say. And thank you for your attention. I'm not sure how I get out of this now. But anyway, Huiping, you're now in charge.
Thank you.